Okay, so today we do the method of elimination, which you should have had before. It's not really that much different in this presentation of it. If you don't remember having it, then this should help you out, right? First of all, it says the name of the lesson in the book, right? Section 7.2 actually is called two variable linear systems, right? And by two variable linear systems, okay, we mean two variables, they're both raised to the first power, right? It doesn't actually mean that you can't use elimination for other kinds of systems, because you can. I mean, we'll actually see later in the class, I think there'll be one that's a nonlinear. Maybe not. But you can do nonlinear. I mean, there are times, you might have done this in Algebra 2 if you did there's like one page on solving nonlinear systems. But you could have something that looked like this. Maybe it would say x squared plus y squared equals 9. And the next line could be x squared minus y squared equals 9. Something like that. And that's not a linear system, but you might use elimination to solve it anyways. So we're not really saying that only linear systems work with elimination. In some cases, you might use it for others. But basically, when you use the process of elimination, what it means is you're going to add these equations together and eliminate one of the variables. Like if in this system of equations right here, if I just add them the way they are, which variable gets eliminated? The y, right? Because it's positive y and negative y. When I add them together, that eliminates the variable. So let's do that. Plus. And that'll give us 4x equals 3. Right? So in that step, y was eliminated. And then you still have to solve for the variable, so divide by 4, x equals 3/4. I'm going to go into more details about these steps. I'm just using this right now to get the basics of. That's what we call elimination, and that's why we call it elimination. Remember, we have to solve not just for x, we have to solve for y. So after finding x equals 3/4, what do you have to do with it? Yeah, you have to plug it into one of these. And if you remember, when we were doing the substitution, I kept saying, when you solve for the first variable, you've got an obvious place to find the second variable. It's that first equation you solved right at the very beginning. Here, not so much. You're going to have to pick an equation, right? And anybody can choose a different equation. You know, you can pick one or the other. It doesn't matter, but you have to pick an equation to solve. You know, if it was me, I think I'm going to pick this one because it's positive y. But you wouldn't be wrong to plug it in the other equation. Right? If I go up here and say y equals 4 minus 2x, so y equals 4 minus 2 times 3/4. Right? So y equals, and this is going to be minus 6/4. So I'll make this into 8/4 minus 6/4, which is 2/4, 1/2. Okay, let's see. Did I do that right? Let me see. No, I did that wrong, didn't I? That 4 is not 8/4. 4 is 16/4. Which means this is 10/4, which is 5/2. Now, honestly, when you're using elimination to solve, you know, the way the book explains it, the way I always explain it too is, you know, you're trying to have opposite coefficients so that you can add the equations and eliminates a variable. But honestly, even if you have the same coefficient, right? If that's a 2x and that's a 2x, you could just subtract one equation from the other, right? If I subtract this equation minus this equation, then which variable does it eliminate? Yeah, would it go 2x minus 2x cancels, right? Let's say I change that to a minus. Then, and now put that result down here. 2x minus 2x is 0. Y minus negative y is 2y. And 4 minus negative 1 is 5. So y equals 5 halves, right? 5 halves, the same one. So, I mean, I think a lot of times, if the only difference between these two is that, I mean, they're the same, and you don't want to like multiply one by a negative one, just subtract them. It's the same thing. But that's the basics, you know, this is a 2-variable linear system, right? It's because x and y are all raised to the first power everywhere. You eliminate, the elimination part is when you add them together and eliminate a variable. If you add them together and don't eliminate a variable, you did something wrong, right? Maybe you were too quick, right? So the steps for doing elimination, this is copied from the book. First of all, most of the time, not all the time, but most of the time, when you start solving a system with elimination, the equations are in standard form. Remember, for a line, standard form is ax plus by equals c, right? You got the x and the y term on one side, you got the constant term on the other side. Usually the x term is first and the y term is second. That's usually the starting point when you're going to do elimination. Okay. This first step where it says obtain coefficients that differ only by sign by multiplying all terms or one of or both equations by suitable chosen coefficients, we didn't do that in the last problem. We already had opposite coefficients for one of the variables. So this step right here is if necessary. I mean, most of the time it's necessary. It's not often that you get the coefficients are already opposite so that when you add them, you cancel a variable. But you don't always have to take that step. So like I said, in the last one, we didn't do it. We definitely then went to step 2 on the last one. We added the equations to eliminate one of the variables, right? And we solved whatever that result was, right? And then we back substituted into one of the original equations. And the check, we didn't check, but it's always a good idea. You could plug it back in, check it out. Okay, we good. So let's say this one here. Do we have opposite coefficients for one of the variables? Not opposite sign, exactly opposite numbers. No, okay, so we need to create that situation by multiplying one or both of the equations by a constant so that they are, for one variable, equal and opposite coefficients. Let's say same absolute value, opposite signs. Right? Which variable do you think in this case would be easiest to set up opposite coefficients? You know, it looks easier here if we just multiply the second one by 3, right? Because I won't have to multiply the first one by anything. So this is the case where we're going to multiply one of the equations, but we don't have to mess with the other one. Okay, so let's multiply this one by 3. Right? And now I'm going to rewrite the whole system. I didn't change the first one, but 2x plus 3y equals 17. And this one now is 15x minus 3y. And then 3 times 17, 51. Okay, So we just created this situation where our coefficients are opposite. Okay, this system, which does not look the same as the system we started with, is called an equivalent system. It'll have the same solution. The graphs of each line won't be changed by multiplying both sides by the same thing, and the solution will be the same. So this is an equivalent system. All right, so we did the first step, move on to the second step, add the equations. 2x plus 15x, 17x, right? These cancel. 17 plus 51, 68. Divide by 17. X equals 4. Okay, that's the first variable. Okay, what's the next step? Using their words, back substitute, right? Okay, so you're going to go back up to. I mean, you could go anywhere, right? You can go up here, you can go over there. Just take one of the equations, and solve. Which one do you think you'd want to use to solve? You know, I could see a case for both of those, right? I mean, this one, everything's positive. I kind of like that. This one, although it's got a negative in front of the y, that's easy to fix, right? That's easy to take this one and solve for y. That'll be y equals 5x minus 17. And then plug that in for the x, right? Y equals 5 times 4 minus 17. Y equals 3. So the point that satisfies the system is 4, 3. Okay, you could check. I'm not going to write it down, but I will check. 2 times 4 is 8, plus 3 times 3, 9, is 17. Good. 5 times 4 is 20, minus 3, 17. So it checks. Okay, so this is one more step more difficult in that we're going to have to multiply both equations by something to get our equivalent system. And at this point, in a problem like this, I mean, you're going to be more variability in the choices. I would say probably in this one, almost everybody's going to do what we did there, right, to solve. You're going to set up the y's to cancel. This one, you got to make a choice. Which variable do you think looks most convenient to cancel? X. You know, we can do X. We'll do X. What I find is that a lot of times you guys tend to always stick with the same one. Even when it's clearly would be more simple to use the second one, you're always kind of just stuck on, well, what am I going to do to make these two cancel? And you don't ever look at the y. You know, look at both. This one, you know, making these cancel, it's all about the same. You know, if one of these had a negative in front of it, I would clearly go for that variable because I already had the negative, but it doesn't. So let's see, if I'm going to make the x's cancel, then I have to multiply 1 by 2 and negative 3, or negative 2 and positive 3, something like that. So how about we'll do 2, multiply that one by 2, and we'll multiply that one by negative 3. And then here's our equivalent system. 6x plus 4y equals 14. Negative 6x minus 15y equals negative 3. Right, so here's our equivalent system. Did I do all the math there? Right? Okay. Okay, add them up. You know, these cancel. These are x is eliminated at that step. 4y plus negative 15y is negative 11y. 14 minus 3, 11. So y equals negative 1. Back substitute. Take your pick, right? How about, I'm going to pick this, I'm going to pick the bottom one if there's nothing else, because at least I've got space right underneath it to show me plugging it in. So let's see, 2x plus 5 times negative 1 equals 1. 2x minus 5 equals 1. 2x equals 6. X equals 3. So that is the point 3, negative 1. And I can check. 3 times 3 is 9, plus 2 times negative 1, that would be minus 2, is 7. Check. 2 times 3 is 6, plus 5 times negative 1, that'd be 6 minus 5, 1. That works. Do you remember doing this in the past? Okay. Okay, I'm not going to carry these systems all the way through. I put these on just to show, right? If you've got fractions, as long as you're going to be multiplying by something, you might as well get rid of the fractions while you're doing it, right? Don't make the fractions equal and opposite. Multiply through, in fact, you could take it in 2 steps, right? Before trying to make the coefficients opposite, just do something to get rid of the fractions. Meaning, find the least common denominator for each individual equation. Like, what would be the least common denominator between 6 and 2? 6, right? 6 doesn't divide into 2. 2 divides into 6, right? So you would multiply this one by 6, right? And then this one, there's only a denominator of 2, so you multiply by 2, right? So here's my first step. 5x. Right. 6 times 1/2 y is 3y. And 6 times 3/2, 9. Right, this is x minus 2y equals 7. Right, so take a step, get rid of the fractions, and then do what we did on the other side. Probably a lot easier than trying to deal with the fractions. And so note, you don't have to multiply each equation by the same thing, right? We're picking the right number for each individual equation. As long as you're multiplying, the equation, all terms on both sides by that same thing, that's okay. But these numbers are almost always going to be different, right? The same thing will go if you got decimals, right? Like we did in the word problem that we did in the homework lesson last night with the interest rates, or the example that we did in class. I mean, if you have decimals and you don't want decimals, then multiply by, it's really, a least common denominator again, but you probably don't see it that way. All of these numbers are written with 2 decimal places to the right of the decimal point. So what do I multiply by to get rid of the decimal? By 100, right? 100, 1 followed by 2 zeros, will move that decimal point over 2 decimal places. Right, so multiply, in this case, that'll be multiplied by 100, and that will be multiplied by 100. It doesn't have to be, right? There could be one that you might have to multiply by 10 and one you multiply by 100, right? That's okay. Just do what's appropriate for the problem. So here's the new equivalent system. 3x plus 4y equals 75. 2x plus 6y equals 90. Right? Solve that. Much easier. So I'm not solving those two, just showing you that step. We're going to solve some more now. solve. Okay. So let's see. What should I multiply by to get my coefficients that I desire? The top by 2, right? Multiply this top one by 2. Right, here's our new equivalent system. Right, in the top we get 12x minus 10y equals 6. In the bottom we get negative 12x plus 10y equals 5. All right, so we set up the equal and opposite coefficients. Next step would be add them up, right? And what happens? The x's cancel and the y's cancel, so we get 0 on the left-hand side. And on the right, you've got 11. So what could that be a sign of? No solution. Right? That's what it looks like when there's no solution. False. So therefore, no solution. Okay, what does that mean in terms of the graphs of those two lines? They don't cross, right? That means you've got parallel lines. Right? Parallel lines don't cross. No intersection. In the book, they use a word for this. They call that inconsistent. Right? I don't really care so much about the word, but you probably see it in some of their directions and things like that. So that is called inconsistent. Right. Try another one. Since that was so fun, let's do another one. Okay, now this is one I'm going to do just because the way when I showed you with the fractions, I said, well, let's make it 2 steps, right? Let's first multiply just to get rid of the fractions, and then we'll worry about making our coefficients opposites, right? So what would I multiply the top equation by to get rid of the fractions? 8, right? So let's do that. Multiply by 8. Okay. And here is an equivalent system. It'll be 4x. Maybe I did do that right. I think actually that's all we need to do. Minus y equals negative 3. And here we've got negative 4x minus plus y, plus y equals 3. I was thinking of a different problem, but so by doing that, we did create our equal and opposite coefficients. So now we add them up, and we get cancel, cancel, cancel. We get 0 equals 0, right? And so what does that tell you about the solution set here? Remember, when we got to a statement that had no variables and it was a false statement, we said no solution. This has got infinitely many solutions, right? One line is laying right on top of the other. Every point on one line is on the other. That's what this is describing here, right? So this is true, which means infinitely many solutions. Okay, I'm not sure. I think the book, if they call this something, they would call that, this is consistent, but it's dependent, is the terminology for this. Sometimes they don't say that, the consistent part, they just say it's dependent solution. Again, it's like the same line. Both of these things here, right, it's the same line. every point on one line is on the other line. Now, if you solve this, like, I think there's one problem in the homework that's like this, right? When you look in the back of the book, this is what you see, right? It says a comma 4a plus 3. And what they've done is they've taken this equation right there. They said y equals, they added the 4x over here. They're saying, so for if x is some real number a, then y will be 4a plus 3. All the points that meet that pattern will be solutions, and there's infinitely many of them. That's what you look at. A, 4a plus 3. They use a. Okay. Okay. So the last two are supposed to show you the two special cases, right? What does it look like when you're solving by elimination and you have no solution, or you have infinitely many solutions? And by the way, when we did the ones where we were actually, getting answers like this, that's called independent. It's consistent and independent. Right? When there's no solution, it's inconsistent. When there's infinitely many solutions, it's dependent. But, I mean, I don't really care about those terms, but they're in there. Okay, now we do a couple word problem kind of things. And, you know, most of the time, if there's a word problem like this, you can bet there'll be a homework problem like this. And it solves almost identical. Okay, in this case, it's talking about airplanes flying into headwinds. Okay, it says an airplane flying into a headwind travels 2,000 miles flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah, which I used to live there for 2 years. Okay, in 4 hours and 24 minutes. On the return flight, the airplane travels this distance in 4 hours. Find the airspeed of the plane and the speed of the wind. Right. So, in the picture, right, the plane is flying into a headwind, right, which means the plane's flying this way, the wind is against it, right? When it goes on the return trip, the plane is flying in the same direction as the wind. So presumably those two are added together, right? The plane is putting so much effort into it, and then the wind is adding to it, so it's going faster, right? And here, actually, the plane is flying into the wind, it's taking away from the speed of the plane, which makes sense. You fly into the wind, you go slower, right? So understanding that distance equals rate, your speed, times the time, we set up two different equations. In both cases, it's 2,000 miles. That's the distance, right? The speed, the rate, when you're flying into the wind, is R1 minus R2. When you're flying with the wind, it's R1 plus R2. Right? The time that it takes to fly, all right, they said when he flew into the wind, it took 4 hours and 24 minutes to get there. That's the time. And when he flew with the wind, it only took 4 hours, right? 24 minutes less. Right? So that is our system of equations. Right? Two variables, two equations. We should be able to solve for the two variables. Okay. So now here's where we will solve it. Okay, and if you look in the way the book solves it, they don't give any of the steps that get to the point where you've got a system to solve. They kind of skip over that part. So I want to do that part because I know there'll be some questions. Let me do this. I'm going to divide both sides of this first equation by 4 plus 24 over 60. Right? So we're going to make this 2,000 divided by 4 plus 24 over 60 equals R1 minus R2. Okay, well, put it in the calculator, see what you get. 2,000 divided by parentheses 4 plus 24 divided by 60. 454, yeah, 454.54. Okay, for this one, divide both sides by 4, right? So 2,000 divided by 4 equals R1 plus R2. And that's easier, that's 500. So now just look at that right there. There's your system of equations in standard form. The variables are all lined up. I'll write it over here. R1 minus R2 equals 454.54. Okay, R1 plus R2 equals 500. Solve. Okay, if we're going to do elimination, do we need to multiply either one of these by a number? No, because the R2s already have opposite coefficients, so just add them up. Right. So this is 2 times R1 equals 954. And probably to be correct about this, I should have said 0.55 or just make it 0.545. And then divide by 2. R1 equals plus 500 divided by 2. 477.273. Okay, and now we have to find the R2. So which equation do you think would make it easier to do that? Probably the second one. I mean, what you could tell is that R1 plus R2 is 500. So you're going to subtract. R2 is 500 minus R1. R2 equals 500 minus 477.273. Which is 22 point, can we figure that one out? 727. There we go. So that's, I think there's one more example, I think. So I don't remember. Looks like yeah, I don't know. Let's see. The demand and supply equations for a flat screen television are, right, now they're giving us P equals for the demand and P equals for the equation. It says where P is the price per unit and X is the number of units. So yeah, the price is different. If the price is different, then the number of units, the demand is different for it, right? If the price is different, then the supply will be different. Okay, so they're saying, find the equilibrium for this market. What do you think they're asking you to do? Set them equal to each other, right? I mean, if P equals this and P equals that, then this equals that. Solve. Now, if I write it like this, I'm going to write it just like they got it there, so I can do work with it. P equals 567, 0.0002x. P equals 492 plus 0.000, how many zeros? Yeah, there's another 0.03x. You know, last class, when we were doing the, when did the ticket sales for the horror movie and the animated movie reach the same? We had equations which are almost identical to that. And that was in the section on substitution. And how did we solve them? We set them equal to each other. So is this really an elimination problem if all we're doing is, I mean, it's kind of hard to make the case for that. That this to me would be an example where I might consider, instead of setting them equal, I'm going to do elimination just like it is right there. Because on one side, I've got the P's lined up and they're equal. So I'm just going to subtract one equation from the other. It's essentially the same thing as setting them equal. Right? If I take this equation, and since they're written in the order they are, I'll just go like this, right? I'm going to subtract this equation minus this equation. Will that eliminate a variable? Sure. So it's elimination. So 0 equals 567 minus 492, 75. And then we've got negative 0.00002x minus 0.00003x, which is, try again, 5x, right? Because you're subtracting. The minus 2 minus 3 gives you a 5 in that decimal place. And then you solve that. You eliminated one of the variables, solve it. Right? If I add the 75 to both sides, or I add this to both sides, I'm going to get 0.00005 x equals 75. So x equals 75 divided by 75 divided by 0.1234. 1,500,000. Okay, well that is asking for, that's the number of units they're talking about. I would guess if they're saying find the equilibrium point, it's probably also in the price per unit. Where should you set the price so that your supply and demand are the same? So we do need to plug it back in to one of these equations and find the P, which is just, they're both solved for P, so that's easy, right? Just plug it in here. P equals 567 minus 0.00002 times 1,500,000. 567 minus 0.12342 times 1500123. A lot of zeros. 537. So that is the price in dollars that if they set these flat screens equal to that price, then their supply should about balance their demand. Okay, so like I said, this is a, you know, it's definitely a systems problem because we've got two equations and two unknowns. Is it really an elimination problem? Debatable. Like I said, we did one in the last section that we solved exactly the same way. We set one equal to the other, and we called that substitution. It doesn't really matter. Okay, oh, I remember. I was trying to figure why I still had one more slide. If you have a choice in which method to use, right? Most of the time, just thinking of the steps that you use to solve, if you have an equation that's already solved for one of the variables, kind of makes substitution the right way to go. If you have them both in standard form with the x's lined up and the y's lined up, it probably makes elimination the right way to go. I mean, out of this one here, this are like 6 of the problems in the homework. I don't believe you do any of them. But which ones of these would you think you would use substitution on because it's already solved for a variable? Right. Yeah, 37, both are solved for y. So I would say that's probably a substitution case. And 38, one of them is solved for y. You know, it's a lot easier just to do substitution than to get the x on this side and line them up and start making coefficients cancel, right? So that's probably a substitution, right? All of the others are already in the form to do elimination. It's probably easier to do that. I mean, if you're given a system and told to solve and it doesn't say how to do it, you know, you do whatever you want. Usually if it's solved for y, do substitution. So this would be elimination, 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 elimination. Right. In the next section, I think, whether we do it right away or not, we start going to like 3 equations and 3 unknowns, and even more, 4 equations and 4 unknowns. And at that point, we're not using substitution and we're not using elimination. We're using matrices in the calculator. And actually, you need them set up like you do for an elimination problem when you do that. And then it's a very easy thing to solve. At that point, you're going to use your calculator. You're not going to use substitution or elimination. You'll just do matrices in the calculator. So I don't remember if I'm pretty sure next class what we're going to do is introduce matrices. We'll work with matrices for a couple of days, and then we'll kind of come back and say, okay, now that we know how to do matrices, how would we go to these kinds of systems and more complex systems using matrices? Okay, that's the plan. And so let's see, we used elimination to solve systems. We interpreted them graphically, and we solved some real life problems. And there's 8 problems here for you.